again, everybody. Here's part 2 of estimating with confidence. We want to take the example that we looked at in part 1 and show you how to do a bootstrap confidence interval for a proportion using the software StatKey. So it's the same question that we were exploring before. What percentage of adults in the United States agree that fathers should have paid paternity leave? So our goal is still to estimate the percentage who agree with some sort of margin of error, although this time it won't be reported as a margin of error, but rather just as a confidence interval itself. Our method is going to be, as before, to gather data from a sample, and remember to take into account all the things we said about the sample before. We also need to remind you that 1,400 of 2,029 adults surveyed agreed that fathers should have paid paternity leave. Now we're going to compute a bootstrap confidence interval instead of using the central limit theorem. So let's remember the bootstrap idea. The sample gives us the best information we have about the population, and what we want to do is use that information to learn about sampling variability. So the idea is that we're going to ramp the sample up. We're going to make enough copies of it to put together until we have something that's the size of a population. Then we can simulate many samples from that population in order to learn something about sampling variability, how it would behave in this particular case. So what we're going to do, our tool is to use StatKey to create a bootstrap distribution. So here we are in StatKey. I need to find in the bootstrap menu this confidence interval for a single proportion. The first thing I have to do is edit the data that's in there. We said 1,400 adults out of a total of 2,029 surveyed said they agree, so we enter that information. And then of course if we generated one sample at a time, we already see that from this simulated population that the computer is creating for us, sampling variability is already at work. But if we generate thousands of samples, our rule of thumb is a minimum of 5,000. If we generate these samples, we'll start to see how sampling variability behaves in this particular case. Now, the dot plot that's being created here is a little bit spiky, and that's really just a result of the rounding that's going on inside of the computer, so don't be concerned with that. To find the confidence interval itself is very simple. We click the two-tail box, which cuts off for us the lowest and highest 2.5% by default, and now we're kind of focused on the middle number. This 95% is the confidence level for us in this bootstrap method, and these are the confidence interval limits down below. In this particular case, why not do something a little bit different? So we'll ask for 99% confidence. So in this case, we see that the confidence interval now is 0.664, 66.4% to 71.5%. So let's see how we report that. So remember, we agreed to use 99% confidence, and here's the confidence interval itself, 66.4% to 71.5%. So we want to communicate this as saying we are 99% confident the percentage of all adults in the U.S. who agree that fathers should have paid paternity leave is between 66.4% and 71.5%. In fact, it would probably be better if we said 66 to 72 to acknowledge that we're not putting too fine a point on the estimate that we're making. It gives us some idea of the role that sampling variability plays when we try to make an estimate like the 69%. Notice that the confidence interval here is a little bit wider this time than it was in part 1, and that's partly because we chose 99% confidence instead. That's all for now. If you have any questions, let me know.